Thank you for the introduction. I'm really happy to be here, to come back to Brasov, to be part of a conference like this. I'm also happy to see that there are more and more developers conferences happening around here. And I think that's really good because there are good opportunities to meet new people and, as Florin put it this morning, get ideas from the other ones, learn from their experiences. I believe this is quite valuable. And this is actually the thing that I'm also looking to get from conferences like this. I try to get inspired by you. So let's take advantage of today and discuss as much as possible during the whole day. What I learned over the years regarding the conferences is that it's really important, at least for myself, that when I go back home and back to work next week, to take all these ideas that I gathered from the conference and try somehow to put them together with the context of my work and try to think of a plan that I can work on, I can implement to improve the workflow, the day-to-day work that I do. And this turns out that, so it comes from the observation that implementation is much more important than ideas. Great companies, great products, successful projects are made by good implementations. And this is also the thing that I'm going to talk to you about today. I'm going to show you how you can create this structure in code which will support the implementation of your architecture. It doesn't have to be clean architecture. It can be any architectural style or any architectural principles which you think are right for your project. But I think it's really important that those get implemented because you may have the best design ideas and the best solutions on how you can deliver this project on time and in budget and have it successfully. Unless those solutions and ideas do not get implemented, you're going to fail. And that's why I think implementation is really important. And let's see how we can create this structure that either supports the implementation of the infrastructure, of the architecture, or it can go a step further and make it like an enforcement. You have to work in this manner. So before I go into that, let me see if this works. I'm going to spend a minute or two to introduce myself. My name is Florin Coros. I am the founder of CodeDesign. We are a company that focuses only on software design, and I really wanted to have the design in the name of the company. And we do this by two types of services. One type is that we take the role of the software architect or the role of the solution architect in the projects of our clients, or we could even take the CTO role for those organizations which for various reasons do not need a full-time CTO. And we try to work with them to lead them towards success, and we try to define what success is for those projects. The other kind of activities that we do is training. We deliver software design training. And what I think, or what we try to do different in the trainings we organize is to take the experience, the project experience that we gather over the years and put it into the training. Each time we find out that a certain approach works in a context, we take that and we bring it into the training. And this thing also happens the other way around, meaning that if we research for a topic on a training, we take it and we will take that learning and we put it in the work we do in projects. When I'm not working, I enjoy traveling. And I also like to play the game of Go. And I can't help myself not to mention, each time I talk to developers about Go, it comes to my mind the historical game between AlphaGo and Lee Sedol in 2016. It was the first time a machine has beaten a human at the game of Go, which was amazing for a Go player at that point in time. And it was like a clear sign that AI is going to take off as it does today. So if you don't know what I'm talking about, you could search on YouTube about this documentary, and it's going to be a nice, worth your time to watch it. Now let's come back to the session from today, so implementing clean architecture. I like to start this one with a simple question. Why is architecture important? Or why do we do software architecture? And this is a question for you, so I'd like some ideas. So we can pass the test of time. The project can survive the test of time. It's a good one. Another reason? Sorry? To have a foundation for the project. That's another good example. Robert C. Martin, yeah, another one. Scalability. That's one of the required behaviors you want to make sure that the architecture, through the architecture that your system is going to have. Robert C. Martin, the guy that made popular this term of clean architecture by writing a few articles and then publishing the book, says that the goal of software architecture is to minimize the human resources required to build and maintain the required system. And what I like about this statement is that basically it has like two parts in it. If you look at it, take a step back, and you look at the last part there is the required system. And this is really important because very often we just go for the most simple solution. And any problem has a simple solution which is wrong. So through the architecture, we also need to make sure that the required behavior of the system gets implemented, like scalability, for instance. Which is really important in, let's say, an online web store, because you want to be able to scale at different moments of the year. If you are building a system for, let's say, energy, then maybe resilience or reliability are also some requirements which you really need to have implemented in your system. And through the architecture, or the goal of the architecture is to make sure that this kind of requirements get implemented. It very often is the case that you cannot factor this in with an optimal cost, let's just put it like that, at the end of the project. So you really need to build for this from the beginning. The other part of this statement is that you want to make it, or the goal of the architecture is that you need to implement the system with the minimum cost. To minimize the human resources. So architecture, it turns out, it has a really strong relation with the money. That's why I have the $sign there. So it tries to, or one of its goals is to minimize the cost related or required to build a system. So we have these two parts. Yuval Lawi, which is not that known. How many of you have heard about him? A few? Actually, Florin only, I think. He's not that Sorry? Ah, okay. So he's one of the few engineers or architects that Microsoft recognizes as a software legend for his contribution to the industry. And he says that success for him is in time, in budget, and with zero defects. And you can get there by doing system design and project design, which is, again, architecture. So with this goal in mind, like optimize the cost, make sure that you're implementing the required system, we start usually to think about the architecture of a new project. And one of the first things that we do when we think about the architecture is to try to decompose the system. And there are many practices, principles, ideas on how you can do this. And basically, what we try to achieve is the right amount of things, those could be called modules, services, components, that build our system. We don't want to have too many. We don't want to have too few of them. You just need the right amount. And basically, what we are doing while we decompose the system is to try to minimize the cost of integrating all the components and the cost of implementing one of them. So you need to be in that minimum to that minimum cost. So there are different ways on how to do this, and at a certain point, we are ending up with a decomposition, and we say, okay, this is how we think the system should look like. This is how the architecture is. And basically, we do this because we need somehow to create a structure that helps us to manage the complexity of the system. And basically, each time we fail on doing this separation of concerns, basically separating the entire system into modules, it happens that the project might fail for technical reasons. It turns out that most of the cases when projects fail for technical reasons, those reasons are coming from this uncontrolled complexity. So separation of concern, the first thing that we want to achieve, turns out to be the most powerful technique that we have in order to build the complex systems that we are building today. And if you think about, let's say, the Gang of Four design patterns, those are very well known. They are nothing else than reusable solutions to very common problems in software design, which, if you apply, you get to a good separation of concerns. The same goes for solid principles. If you follow those principles, then you will get to a system that has a good separation of concerns. And basically, this is the end goal that we want to achieve through architecture. So from the architecture effort, we end up with this separation of concerns, which can be described or described to different methods, different methodologies. Here I have a few examples on the slide. The one in the middle is the well-known three-layered architecture. And with this style, we say we are going to put all the business logic code, which is the most important code we have, because that's very particular to our application, is where we write all the business flows that happen or that should execute behind our use cases. So we put this in the middle, and then we want on top to have the area of concern that deals with how the user is going to use the system, is going to interact with the system. And then at the bottom, we are going to have the data access layer, and that's where the code that deals with how we store data and retrieve data is going to be written. And we imagine with these three layers that we are going to have a good separation of concerns, and basically that's the architecture. There are, of course, different variations of it. We can have more complex systems, more layered, more layers or fewer layers, so it can differ from system to system. Also, part of the architecture, we usually come with vision, with a design on how the dependencies between our components and classes are going to look like, how those dependencies can be created, which are the rules that govern everything. And basically, from the architecture effort, we end up with a bunch of diagrams, rules, and documents. And then having this, so we have the architecture on one hand, and then we go to the development team and we start to implement the system. And we start to write the code. And after a few months, we write even more code. And then if we take a step back and we just look to whatever we have done so far, in many cases, it happens that the business logic is no longer there. It's like it vanished. Even if we said, okay, this is the most important layer that we have, it's like the code that's very particular to our application, it somehow happens that we end up with this gap between the architecture and the code. We have some business logic in the presentation layer because that's very convenient to validate the user inputs right there. We have some business logic mixed with code that does data access because it's more performant to do data aggregations and filtering in the database. So the separation of concerns that we had on the left, on the architecture diagrams, is no longer in the code. And when this happens, the architecture basically has failed. It makes no use to have a bunch of diagrams if those do not get reflected into the code, because the diagrams are not going to be executed. The code is what matters. The code is the thing that we need to change when we want to add new feature or to change some features. So it's really important to close this gap. And basically, this is what I'm going to show you in the next part of the talk, on how we can create this structure, which somehow makes it that it's going to be very easy to write the code that follows the architecture, and at the same time, it makes it hard to write the code that doesn't follow the architecture. So you have such a structure, then it means that when some new developer comes to the team and it tries to make a connection from the, let's say, some code in a layer which is part of the presentation layer, and it tries to make a connection to the database, that's not going to be easily possible because of conventions, because of the structure which are there. You're maybe not going to be allowed to make a reference to that assembly or to that code package which is able to connect to your database. That's one example. So we want to have this structure in the middle. Before we go into it, I'm going to talk a little bit about clean architecture, so we have like a common vocabulary for the next slides. So the structure that I'm going to show you tries to enforce the rules from the clean architecture. So let's see which are the rules. So with a clean architecture, we have this way of representing the areas of concerns. So we are using these circles, these concentric circles. I also like to look at this picture like it would be, it would have a 3D view, like there are disks, one on top of the other. So at the bottom, I have the larger disk, which represents the frameworks. That's the code that belongs to the frameworks that I'm going to use. And at the other end, on top, I have the business logic. That's the logic of my use cases and the entities that are on top. And the clean architecture comes with this way of representing the separation of concerns, and it comes with a very important rule on how dependencies can be created. So this is also called the dependency rule. And the dependency rule says that you can only have dependencies from the exterior layer towards the interior one. And if you hear some presentations from Robert C. Martin, he often said that with clean architecture, you want that your application code does not depend on the frameworks, but the frameworks depend on your application code. And when I first heard this one, it seemed very strange, because what do you mean, like I won't depend on my frameworks? Because if I'm using, let's say, an ORM to do data access, like Hibernate or Entity Framework, then I am going to use the classes of that library to do the data access, so I'm going to depend on them. And the other way around, it's even more strange. What do you mean that Entity Framework should depend on my application code? Because when they've written the Entity Framework, they had no idea about my application. So let's see how this actually works and how you achieve this. Another observation here is that by having this rule on how dependencies can be created, so from the frameworks to the application code, the clean architecture directly targets one of the objectives of the architecture, which is minimize the cost. And by making that the business logic, which is in the center, does not depend on the frameworks, it means that it won't change because of external reasons. It will have less reasons to change. It will only change because of its own reasons. So it's somehow protected to the number of changes. You don't have the triggers, changes being triggered one by the other into the business logic layer. So let's see how it works. And here I've taken one example from Uncle Bob, which uses three classes. Two of them, the presenter and the controller, are from the green layer, and then we have a use case implementation class, which is from the interior layer. And over here with this blue arrow, this one, we have a representation of the flow of control. So basically, the controller would be that code that takes the user inputs, user interactions, Then it goes to the business logic layer to execute the logic of the use case, and then it goes back to the presenter to show some results of the action on the screen. So the flow of control is from green, orange, back to green. If we look now to the code dependencies, we have the controller taking a dependency on the use case implementation. If we make this example more specific, and we say, let's imagine the code of an online store like Emag, for instance. On the controller, we could say we have the code behind the buy button, or the code behind the web request, which is called when the user presses buy. So over here, we somehow need an instance of the class from the business logic layer. We could say it's the ordering service, because it will place a new order when the buy button is being pressed. So the code in the controller would look like something like new presenter or get a presenter instance, and then it's going to call place new order method, and in the input parameters, it gets the data that the user has filled in. So that's why we have this code dependency here. Now, if we zoom into the place order function, over there we do some logic like check the stocks, the price, and so on. And then at a certain moment, we might need to show the user some results or a message, something like your order has been placed, or you cannot place this order because you're not 18. So the ordering service, place new order function, will need to make a call to the presenter, to a function on the presenter, like presenter show message. And this makes a code dependency, like this one in red, which is not conforming with the dependency rule in the clean architecture. That's why it's in red in the diagram. So we need somehow to invert this dependency. And how do we invert dependencies? Which principle comes into mind when we think about? Sorry? DI, from dependency inversion, not injection. It's a very common confusion between dependency inversion and dependency injection. There are quite different things. But the dependency inversion, which is the D from the solid, basically says you can invert any dependency by creating an abstraction. And this is what we could do here. So now we are having this use case output abstraction, this one here, which basically represents the needs of my application from the frameworks, from the presenter. So it abstracts what my application needs. And now the place new order function will no longer depend on the presenter directly. Actually, it wouldn't have a code dependency to it, because it will now call a function from this interface. And the interface belongs to the orange layer, to the business logic layer as well. The presenter takes a dependency on the interface because it implements it. So we have now inverted the dependency, and we have this new diagram that now conforms with the clean architecture. So in a nutshell, this is like the key rules or the key principles behind the clean architecture. I also have here another abstraction which is created from the comparing with the previous image. It's not because I wanted to invert that dependency, but it's mainly because it's good to have the interaction between layers to be done through abstractions. It also reduces the cost of change. So with this in mind, let's go and see how we can create this structure. So we want a structure in code, which should make it very easy to write a code that follows the architecture, the good code, and at the same time, it would make it very difficult to write the code which doesn't, so the bad code. And there are three key techniques that I'm using to implement this structure. The first one is to hide the external frameworks. And one of the additional benefits that I'm getting from this is that now I achieve a certain consistency on how my code is being written when interacting with those frameworks. So basically, each time I'm, if I would, let's say, hide the framework that I'm using to do data access, then it means all the API of that framework is going to be in one place. And then I would have consistency on how data access is being done through my application. The second technique is to use references between assemblies, or I would say references between jar files for Java or packages in the JavaScript. So these units of deployment. So I would use this to enforce the rules on how references can be created, how which assembly is allowed to make a reference to another assembly. And it turns out that these units of deployment, the dependencies between them can be easily checked. Mainly the code won't compile if you have circular dependencies. It's easier to do automatic static code analysis, so you automatically check these rules in your continuous integration. You could also use reflection or other tools to write tests which validate that these rules are being followed. Or even if you don't automate anything, it's going to be very visible if you're just reviewing the code, because when you have a new dependency, that's quite visible. And then the third technique is to enforce the usage of constructor dependency injection. This not only that encourages programming against interfaces, but it will also help in making an order on how dependencies between the classes are going to be created. For instance, you won't be able to make circular dependencies between your classes, because if you only use constructor dependency injection, you would end up in an infinite loop eventually, and then things will break. So now let's take an example. And for the rest of the slides, I'm using this color coding. So it matches the diagram with a clean architecture. So on top there, I have these boxes which represent assemblies that are part of my business logic layer. That's why they are in orange. And usually we might have more than one. Then we have in this diagram, which is a very simple example for logging, how we would implement logging. We have the log4net assemblies, so the external library that we are going to use for logging with blue. And the most trivial and most common way of doing logging is you just take a reference to the external library that you're going to use, directly use the API in your code. And this is against the dependency rule from the clean architecture, where we don't want to take the references to frameworks, so we need to apply dependency inversion principle and to have something like this. So in this diagram, I have created this logger interface, iLogger interface over here. And now it is colored in orange because it belongs to my business logic layer. Basically, it describes my application needs from logging. And it will only change if my application needs of logging change. Then I have another class over here, which is the logger in green. So it's part of that adapters layer that implements the abstraction I created by using the external library. So now I am conform with the clean architecture rules. I'm using logging only because it's a very simple example to explain this. It's not because you would probably do something like this for logging. And also, in this diagram, one thing to observe is that I created two new assemblies from the previous. And the reason I'm having these two assemblies is to enforce those rules and to create the structure. So basically, let's take them one by one. So this one in green, the logging. This is here because I want to have a rule that the logging assembly, the one in green, is the only one allowed to take a reference to the log4net. No other assemblies in my system can do that. No other assemblies in my system know that I'm going to use log4net to do logging. So that's the reason I have this one here. And then I have another one here, the logging contracts. And the reason I have this assembly is because I want to make sure that the code written in my application components, so the most important code I have, only depends on abstractions. So I don't want it to have a dependency on the logging assembly, the one that does the implementation, the green one, because if it would have a dependency here, it means it could directly depend on the implementation. So I want to have here a more strict rule that says all the code here is going to depend on abstractions which are part of the same layer. And the reason I'm creating like a contracts assembly is because if I have more application components assemblies, then I need some level of reusability. All of them will need this iLogger interface. Now, this might seem a bit too much for some scenarios or for some systems which are maybe not that complex. So we could look at the version that's a little bit simpler. So we could do this compromise. And basically the compromise here is that we have moved the iLogger interface into the green assembly, and we reduce the number of assemblies. The risk that we are taking by doing this is that now the code here, the application components code, would basically depend, could actually directly depend on the implementation. And we could reduce this risk by making all the implementation classes in there to be internal or private. So this makes that all the public types in the green layer assemblies are actually abstractions that belong to the upper layer, to the business logic layer. So it's a way to simplify this. Now we can take this approach and implement it for all the external libraries that we are using. And we create like a gateway, like a set of assemblies which hide the external libraries that we are using. And by doing this, as I said, we create consistency on the way the code is being written, but we also address a very common conflict in software design, and that's the conflict between the one that creates and publishes a library and the one who will take that library and use it in its own application. The one that publishes the library wants to make an API for it that's as generic as possible, that fulfills many types of applications, because the more applications are going to use the library, the more successful the library is. But the guy that takes the library and wants to use it in his project, he doesn't care about the others. He just wants an API that's very specific for himself. So he would want to have it thin and nice for his own needs. And by doing this adapters layers, basically we are addressing this conflict. So we are creating these APIs that are very specific for our application, and they will only change for our application needs. And here I have an example on how you can do this for entity framework. So basically, we hide here the ORM. It could be entity framework or something else. And by doing it, we enforce a separation between data access and the business logic. Because now in the business logic over here, you won't be able to make a connection directly to, you won't be able to directly use the ORM. You need to go through this layer of abstraction. And this, again, makes consistency on how you do it. I won't go into many details on how you would implement this for entity framework. There are a few technicalities there, but that's not that relevant. Instead, one observation is that if we want to have this ability to create diagrams like this one, which are a bit more complex than logging, so we want to be able to set the rules on how references can be created to sustain the principles and the rules that we have in our architecture, in our design. It means that we need to have this flexibility, just to say, okay, I want this reference to be from this assembly to this assembly. And if you think about how you would implement this with dependency injection this time, it would be a bit difficult, because if you're using compilable code to configure the dependency injection container, it means you need to have some code that says, okay, for this interface, I'm using this class as an implementation, register this into the container. So there are those large source code files which just do registrations. And even if you split that into more files and more assemblies, Those assemblies which contain the source code of this will basically reference everything, and that's going to be quite problematic. So meaning you won't have the ability to do this right. So the solution to it would be that you, again, apply the same technique and you hide the dependency injection framework this time. In my diagram here is the Unity container. So now I'm creating this annotation, this service attribute, which is an abstraction for my application. And I'm basically using it to specify as a declaration that a certain class should be registered into the container, the dependency injection container, as an implementation for the interface, which is given as a parameter here. So basically, we are implementing this type discovery mechanism. So when the application starts, somewhere on the main function, before it's ready to receive requests from the users or the other systems, we are scanning all the assemblies that build the application, all the types. We are looking for these attributes, and we do the configuration of the container. And then it means that the implementations can be either private internal classes belonging to other assemblies which are not referenced. So we have this flexibility to have diagrams like this one implemented. And of course, all we need now to reference the assembly from the adapters layer where this service attribute lives. The advantage by putting in place this kind of structure is that we make all of our classes to pretty much look like this one. So it has dependencies towards abstractions. All of those repository price calculator, approval service, those are abstractions. Some of them, the implementation of those are not even visible, are not even accessible to the code or to the assembly that contains this code. For instance, the implementation of the repository would be somewhere else, and you won't have a direct reference to it. And you can enforce this because now you would control the dependency injection. So you can say, I won't register in the dependency injection types that are not, you cannot receive references to them through interfaces. Then all the abstractions, so the dependencies of the class are now part of the public interface of my class. And this again comes because you now enforce constructor dependency injection to be used. So you have to make them visible in the constructor. This helps with testing and maintainability further. So basically, we are creating these patterns in the way the code is being written. And the patterns are now supported by this infrastructure. So let's sum up. We do architecture because we want to reduce the cost of change, and we want to make sure that we are implementing the required system. From the architecture efforts, we end up with a separation of concerns. We describe that to diagrams and through documents. And then what I usually do to make sure that the architecture gets implemented is to build this structure which makes it easy to write a code that follows the architecture, makes it hard to write a code that doesn't. And I use 3 techniques: hide external frameworks, enforce rules through references, and use only constructor dependency injection. The data access and the application boot are the first building blocks that I'm using to build these infrastructures. They are available on GitHub, so you can go there on the iQuark account. iQuark is an organization I co-founded years back. So you can go there and see the code, get inspired on how to implement this in your projects. Or if you're doing .NET Framework, you could get them from NuGet. They are production ready for .NET Framework. So what are your questions?